Hello and welcome. My name is Ed Lima. I'm a product manager in the AWS AppSync team, and this is Powers Modern Serverless Applications with GraphQL and AWS AppSync. Here's what we're going to talk about today. We start by quickly leveling up on GraphQL as a technology. Then we'll talk about AWS AppSync and how it leverages GraphQL to provide a powerful and flexible serverless API solution. We then showcase some unique features, capabilities, integrations, as well as security options built into the service. After that, we go through powerful developer tools that allow developers to create their AppSync GraphQL APIs, improving development agility, velocity, and flexibility. What is GraphQL? GraphQL is a query language for APIs and a runtime to fulfill those queries. It's completely unrelated to graph databases as data is not persisted in the GraphQL layer. GraphQL has both an API component to expose and access data, as well as a compute or a runtime component where developers can customize their own business logic directly at the API layer. I believe images are better than words to describe one of the main advantages of GraphQL. Let's imagine we have some sort of front-end application where users can access their data via web browser and mobile. It can be anything: e-commerce, social media, banking, collaboration, chat apps, blogs, pick one. Modern applications expose data from backend services using application programming interfaces. APIs are a very important construct that connect your front end to the backend, allowing applications to interconnect, interact, and integrate with internal or external services from all sorts. With traditional APIs, multiple endpoints are exposed. These endpoints can access the same data source with different access patterns and requirements, or each endpoint can access a separate data source. For example, we can use three different databases. Imagine one for orders, one for products, and one for inventory, if we're talking about an e-commerce application. Imagine we have users accessing the data from different devices, mobile phones and laptops. Users start the app, log into the system, and want to get their data. In order to do so, they need to access the API endpoints to load the required data to their devices. With traditional APIs, loading the data is done sequentially. First, I need to access my endpoint A to retrieve some of the data and populate the application user interface accordingly. The response payload in traditional APIs is static. No matter the device I'm using, I'm always going to get the same payload. Maybe it's a big JSON object with tens or even hundreds of fields. Mobile devices have smaller screens, so they need to display less data. A laptop or browser have more screen real estate, so it can display more data. However, since the response payload is static, both devices receive the same amount of data from the API endpoint. All users will always get the payload in the same format, even with fields they don't require, no matter what type of client or device. The front-end application has to manually pick and choose the fields in the JSON payload. It needs to display and discard the rest of the data. Maybe there's data needed the mobile app or the web browser needed. This data also needs to be discarded. This is called overfetching data. Well, we successfully loaded part of the data in our user interface, but there's more work to do. Now we have to load more data to populate the rest of the UI. Maybe there was a specific ID I retrieved from the endpoint A I needed to pass to endpoint B in order to retrieve some more data. So while I overfetch data from endpoint A itself, I also underfetch data. So I needed to make a second API call to endpoint B to get the full data set I needed. So depicted here as the green and blue shapes. Same as before, since the response payload is static, both devices receive the same amount of data from the API endpoint, even if the mobile device requires considerably less data. The front-end application has to manually pick and choose the fields in the JSON payload. It needs to display and discard the rest of the data in the response. Finally, I call the third endpoint to get the rest of the data. Now my data is fully loaded and my application users can interact with their full data set. With traditional APIs, in order to get the data that I needed, I had to make 3 API calls because I was either overfetching or underfetching data for both device types. Now let's take a look at GraphQL. With GraphQL, I have a single API endpoint exposed to all clients, and I only need to make a single API call. The client defines the data it needs, and data is retrieved from multiple data sources automatically for me. The mobile app reaches the exact same endpoint and receives a customized payload with only the data fields it requires. As you can see, the payload sent to the web app and the payload sent to the mobile app have different sizes, which means network calls are optimized and the payload reduced according to the client. We can make an analogy with a pizza. With traditional APIs, you would order a pizza and it comes with all toppings. You have to remove them later. This is overfetching. With GraphQL, the pizza comes just with the toppings requested. Nothing more, nothing less. Which means it saves you time and bandwidth. We can also have other APIs and microservices as data sources, as we're showing up here. You can use GraphQL APIs as a single interface to connect and aggregate multiple microservices in your application, acting as a data layer to connect and communicate seamlessly with multiple backend services. GraphQL is agnostic to data sources technology, allowing you to easily abstract them for different applications. You can have any type of data source behind the GraphQL API. SQL, NoSQL, HTTP, REST APIs, it doesn't matter. It's perfectly fine to mix and match different databases and other APIs behind a single GraphQL API. Basically, with GraphQL, clients and API consumers get exactly the data they need, with less networking calls. Nothing more, nothing less. Now let's talk about some GraphQL concepts. GraphQL, as the name describes it, is a data query language for APIs. It is also a runtime to fulfill those queries. GraphQL expresses the declarative language for requesting data from your application backend. It uses a type system that allows you to understand data requirements and get meaningful error messages. Make it easier to use and prototype. You define the GraphQL API with a schema based on a schema definition language or SDL. The schema is where you define different types, such as the user type and its properties of fields, like we can see here. In this schema, you can also define specific operations. There are three types of GraphQL operations: queries to read data, mutations to modify or write data, and subscriptions. Subscriptions are linked to mutations and allow to send real-time notifications to subscribe clients whenever data is changed by a mutation. In green, there's what we call selection set. The selection set represents a collection of fields you define to be returned in a GraphQL operation. The ability to define selection sets is a powerful feature of GraphQL, as we saw in the previous slides. The client defines the data it needs. For instance, if I only need the ID and a title, I can only define my selection set with those two fields, so my client only gets the data it needs. And that's valid for all operations. I can execute a mutation to create data and ask the GraphQL API to return just the ID and the date for a post, so I can use it in my application. No need to pick and choose fields from a static JSON payload. The response is dynamically generated by the GraphQL backend according to what the client defines. But what's the best way to use GraphQL on AWS? Well, you could run a GraphQL server, but servers are so 2014, aren't they? With AWS AppSync, you can build scalable and robust applications over GraphQL with both real-time and offline capabilities. Best of all, no servers to worry about. It's important to understand AppSync is first and foremost an application data service with real-time and offline features implemented over GraphQL with additional capabilities such as built-in authorization and conflict resolution. It's not simply a GraphQL API proxy. You can have all sorts of applications: enterprise, mobile, web, IoT, accessing a GraphQL API powered by AppSync to interact with different data sources in your AWS account. AppSync allows you to power your application with the right data from one or more data sources at global scale. It simplifies application development by letting you create a flexible API to securely access, manipulate, and combine data from one or more data sources. That can be databases or other APIs. AppSync APIs can access data directly in DynamoDB NoSQL tables or our serverless databases or Elasticsearch clusters. Applications can access anything in your account using Lambda functions or even REST APIs with HTTP resolvers. You can easily have both REST and GraphQL in your backend behind an AppSync API. You can also use HTTP resolvers to connect directly to other AWS services, such as step functions or Event Bridge, via the regional endpoints, which means it can be used as a GraphQL facade to any AWS service. It's also possible to use local resolvers. Think of it as a pub/sub channel where data is not persisted. To get started, you need to model and define your data in a type GraphQL schema. The data model in the schema tells API consumers what data can be exposed to authorized clients, with automatically generated API documentation using something called introspection. As API can be defined with a simple and understandable type schema, it allows you to better organize your data and understand the data flow between different downstream components of your API. We mentioned GraphQL has a built-in compute or runtime component where developers can customize their own business logic directly at the API layer. These components are called resolvers, and they provide the logical glue between the data defined in the GraphQL schema and the data in the actual data sources. They are called resolvers because they are built-in functions in GraphQL that resolve types or fields in a type defined in the GraphQL schema, linking them with the data sources. Then, as mentioned before, we have the data sources, where the data is actually stored. So these are the main components in an AppSync API: the GraphQL schema, the resolvers, and the data sources. Resolvers can be of two types: unit resolvers or pipeline resolvers. You can think of pipeline resolvers as a collection of unit resolvers that are executed sequentially. AppSync executes resolvers on a GraphQL field, as we discussed previously. In some cases, applications require executing multiple operations to resolve a single GraphQL field. With pipeline resolvers, developers can compose operations, orchestrate, and execute them in sequence. In this example, the pipeline resolver is calling a SQL database to retrieve some data. Then it saves it to what is called the stash. The data in the stash persists throughout the pipeline. The response is then passed to the second function in the pipeline that connects to a NoSQL table to perform a second operation. Finally, after the stash is updated with data from the previous steps, the pipeline calls a third data source, maybe a Lambda function, or an AWS service like EventBridge to execute the final operation, all in a single GraphQL call, interacting with three different data sources, saving network bandwidth and resources. AppSync leverages VTL, or Apache Velocity Templates, to provide a lean and fast compute runtime layer to resolve GraphQL queries or fields. It uses VTL internally to translate GraphQL requests from clients into a request to a data source, as well as the response. You can also use direct Lambda resolvers, which make VTL templates optional when integrating AppSync with Lambda. Direct Lambda resolvers make it easier to work with Lambda and GraphQL and AWS, giving you more flexibility when developing GraphQL resolvers on AppSync with Lambda data sources, using your programming language of choice to define a GraphQL resolver business logic. So let's take a look at the specific scenario, an e-commerce system. Imagine there are different services in your application backend accessible via different technologies. User data is stored in a highly scalable NoSQL table. Orders are accessed to a REST API. The current inventory stock is managed through a Lambda function, and price information is in a SQL database. Usually, client applications would have to make 4 or more different calls to each one of those services, exposed to different API endpoints to get the data they need, thus increasing complexity on the client side. In these 4 networking calls, clients would also most likely overfetch or underfetch data, as different data sources would send an entire payload with some data I might not need. What if I could access all the data I need from a single endpoint with a single network call? With AppSync and GraphQL, it's exactly what you can do. An AppSync GraphQL API combines the data from all these different services into a single payload the client defines, allowing to fetch only the data required for a client defined in the GraphQL selection set. The data is retrieved from multiple data sources automatically for me, and these data sources can be anything: SQL, NoSQL, HTTP, it doesn't matter. GraphQL is agnostic, so you can use the best tool and the best technology for the job in your backend. The client just sees a single constructed payload, receiving user profile data from Dynamo, order details from API Gateway, as well as seamless injecting specific fields with inventory availability and price data from Lambda and Aurora, all with a single network call and from a single API endpoint, abstracting all the backend complexity. Front-end or API consumer teams can add new features or applications without waiting for a specific backend team to implement new APIs. Since GraphQL is self-documented, introspection makes it easy for front-end developers to learn what data is available from a single unified GraphQL API endpoint. Now moving on to security, we have our GraphQL application users and API consumers. It's essential to verify users are allowed to access the API, as well as verify if they have proper permissions to access the data, what you can do, and who you are. It's very important to authenticate and authorize API consumers with proper access controls, so they can only access what they have permissions to. And the API service needs to be flexible enough to meet all sorts of different business requirements. With AppSync, you create a GraphQL APIs that your applications interact with over the internet. While the API endpoints are publicly reachable, they never allow unauthorized access. A method of authorization, a token in the request header, or signing the request itself with AWS credentials is always required to access your API. AppSync provides great flexibility with multiple supported authorization modes. API keys, Cognito user pools, if your users are managing a highly scalable user directory in Cognito, OpenID Connect, if your users are managed via an external OpenID Connect provider, IAM, and while not a direct authorization mode, it's possible to have custom authorization with AWS Lambda leveraging pipeline resolvers. However, we have some improvements in mind. In the near future, we plan to make Lambda as a first-class authorization mode to make it easier to implement any type of custom authorization business logic in AppSync using serverless functions. Stay tuned. AppSync must have a default authorization mode defined globally. It's possible to add additional authorization modes in the same API, as well as mix and match these modes, linking specific authorization providers to types, fields, or operations in the GraphQL schema. In order to do so, you can use AppSync-specific directives to configure authorization and security at your data definition directly in the GraphQL schema. Here's an example. Imagine you have a flight type defined in your schema, and Cognito user pools is the default authorization mode in the API. Maybe you need to expose specific fields in the flight type for guest users who connect using API keys, and some other fields to IAM users or services who use AWS credentials to connect to your API. As a default authorization mode, users authenticated by Cognito can access all flight data. It's even possible to configure specific groups of users for fine-grained access as an option in the directed definition. In this case, the frequent flyers group can access all the fields. If a user connects with an API key for public access, it'll only be able to retrieve the flight ID, departure airport name, and code. All other fields will be returned as null. Even if the client doesn't have access to all fields, it still gets partial responses, allowing the client to access only the data it has permissions to access, depending on the authorization option it uses. Last but not least, if a user connects with IAM credentials, it will only be able to retrieve the flight ID, arrival airport name, code, city, and locale. Multi-auth in AppSync provides great flexibility, as I can define security and authorization access directly in a GraphQL schema, allowing to lock down entire GraphQL types or operations just easily. Now let's move to real-time. You can use AWS AppSync to enable scalable real-time collaboration use cases. AWS AppSync takes advantage of GraphQL subscriptions to perform real-time operations by pushing data to clients that choose to listen to specific events from the backend. You can have thousands or millions of clients subscribe to a specific mutation in AppSync. This means that you can easily and effortlessly make any supported data source in AppSync real-time with connection management handled automatically between the client and the service. A backend service can easily broadcast data to connected clients, or clients can send data to other clients, depending on the use case. Whenever a client invokes a GraphQL subscription operation, a secure WebSocket connection is automatically established and managed by AppSync, and will remain constantly connected to your backend, allowing users to receive real-time data from any supported AppSync data source. But how does it work in practice? After authorization clients make a subscription call linked to a specific mutation, a WebSocket connection is established for 24 hours, providing a secure channel between the client and AppSync. Clients can be subscribed to multiple mutations, and the related subscriptions all share the same WebSocket channel. In this example, we have a single DynamoDB table, but it works the same with any supported AppSync data source. If a client executes a mutation, for instance, create order or create message or update comment or delete task, it reaches a single GraphQL API endpoint in AppSync. AppSync will then perform authorization checks and execute any business logic defined in the resolver, then send a request to DynamoDB to create an item in the table. After the data is saved to the data source, AppSync automatically broadcasts the data to all subscribed connected clients. Each client can have a different selection set defined. For example, a client might just need an ID, while the other client defines an ID and a description, which means different clients just receive the data they need. Arguments can be defined in the subscription, which means if I don't want all clients to receive a broadcast, I can define clients listening for just a particular ID in the subscription. In the same sense, this can be done one-on-one, so only one client receives subscription data. Think of a chat app where one-on-one conversations are private and only users in the chat can receive messages. So we saw how clients can send data to other subscribed clients, either one-on-one or one-to-many. What about backend data? How can I push backend data to connected clients with AppSync? It's possible to have a backend process, for example, sent by SNS, SQS, Event Bridge, Step Functions, or IoT, invoking a Lambda function that executes a mutation against AppSync. Usually, backend processes on Lambda can easily leverage IAM to call AppSync. Same as before, AppSync sends a request to DynamoDB to create an item in the table. And again, same as before, after the data is saved to the data source, AppSync automatically broadcasts the data to all connected subscribed clients. As you notice, AppSync needs to be aware of a mutation in order to push subscriptions data. Or if there's an out-of-band process updating DynamoDB in the backend without sending a mutation to AppSync. In that case, AppSync is not aware of the mutation and will not send data to subscribed clients. If there's a requirement all changes to DynamoDB, even out-of-band, need to be pushed to connected clients, we can leverage DynamoDB streams, invoking a Lambda function that issues a mutation to AppSync. So we're not saving the data twice or overwriting the data previously saved on Dynamo. We can use a local resolver for the mutation triggered by Lambda. Local resolvers are internal to AppSync and can work as a pub/sub channel where no data is persisted. Clients subscribed to the mutation linked to the local resolver are then notified about the out-of-band changes in the DynamoDB table and receive the required data automatically. AppSync empowers real-time collaboration with simplicity. Real-time data, connection management, scalability, fan-out, and broadcasting are all handled by AppSync, allowing you to focus on your application business, use cases, and requirements instead of dealing with the complex infrastructure to manage WebSockets connections at scale. You can visualize metrics on CloudWatch, a number of active connections and subscriptions, status, errors, and more. AppSync also has built-in offline capabilities. If you're using a mobile app and for some reason you get to a place without coverage, such as a tunnel or a subway, the AppSync client can use optimistic UI features to enable users to keep using the app seamlessly, adding and editing data like nothing happened. When the client gets back online, the data is automatically sent to AppSync and update the backend data source behind the scenes. Full end-to-end support for offline scenarios depend on a client with offline and synchronization capabilities, as well as support on the backend side. AppSync provides two available options when it comes to clients: the Amplified Data Store and the AppSync SDKs. The data store is a queryable, local, on-device data store with a familiar local-first programming model that abstracts GraphQL on the client side, which means front-end developers don't even need to be familiar with GraphQL to get started. Supports JavaScript, React Native, iOS, and Android, leveraging different local storage technologies depending on the platform. The data store detects when the client is offline and automatically synchronizes data behind the scenes with DynamoDB backends via AppSync when the client comes back online. Since it's familiar to a full-fledged local database, it's more powerful and flexible than a local cache. The AppSync SDK provides a local cache that supports all types of AppSync data sources. It supports the same platforms and storage options as the data store. The SDK detects when the client is offline, caching data, and automatically synchronizes the cache with the GraphQL Cloud API when the client comes back online. As a managed service, AppSync also provides powerful integrations with other AWS services to provide important features such as enhanced protection, tracing and observability, insights from the GraphQL API operations, as well as server-side caching, all managed for you so you don't have to manage yourself. Any of them can be enabled with a simple click of a button in your API settings. AppSync integrates with AWS WAF, which is a web application firewall service that helps protect AppSync GraphQL endpoints against common web exploits that may affect availability, compromise security, or consume excessive resources. X-Ray enables full end-to-end tracing support for AppSync APIs. You can enable X-Ray in your API to get an end-to-end view of the entire request and visibility on the performance bottlenecks in components and modules. CloudWatch allows you to get logs and metrics and effectively monitor your GraphQL API. It also provides a powerful feature called CloudWatch Log Insights, allowing you to get very useful information about your API usage. Insights enable you to interactively query, search, and analyze your API usage. Best of all, there are useful sample queries that allow you to get started in no time. For instance, you can visualize the most frequently invoked operations and resolvers in your AppSync API to help understand and identify hotspots. Finally, AppSync server-side data caching capabilities reduce the need to directly access data sources by making data available in a high-speed in-memory cache, improving performance and decreasing latency. AppSync hosts and manages internally Elastic Cache Redis instances in the AppSync service accounts, so you don't have to worry about that. Our customers often tell us how AppSync and GraphQL enables to increase and improve development velocity, allowing you to ship products and applications faster in weeks as opposed to months. However, it's also very important to have powerful development tooling to do so, and that's where the Amplify and the AWS CDK come in. The Amplify framework provides a set of developer tools, libraries, and UI components, as well as a powerful command line interface to build and manage cloud backends. Easily integrated with your iOS, Android, Web, React Native, and Flutter apps, as well as web hosting console service to deploy and host web applications. There is also a new admin UI that allows you to manage users and data in the Amplify data store, backed by Cognito, AppSync, and DynamoDB. In my opinion, one of the most powerful Amplify tools is the GraphQL Transform. GraphQL Transform provides a simple-to-use abstraction that helps you quickly create backends for your web and mobile applications on AWS, all based on the simple GraphQL schema you define. The Transform uses directives that you can associate with the types or fields in the GraphQL schema. The Amplify CLI automatically generates and deploys CloudFormation templates and stacks to create all the backend automatically. Here you can see AppSync, Cognito, DynamoDB, and Elasticsearch all deployed, integrated, linked, and configured with built-in AWS best practices using just 3 specific directives. The AWS Cloud Development Kit, AWS CDK, is an open-source software development framework to model and provision your cloud application resources using familiar programming languages. You can leverage high-level CDK constructs and deploy an AppSync API with a DynamoDB data source with just a few lines of code, as you can see here. Amplify takes an opinionated declarative approach. What do you want? While the CDK takes an imperative approach, how to do it. At the end of the day, both generate and deploy CloudFormation templates that can be fully customized. You can choose the best tool for use case and development style. GraphQL developers have specific preferences when developing GraphQL APIs. There are 2 approaches most currently used: schema first or code first. With schema first, the GraphQL schema file based on the schema definition language, or SDL, is defined and used as the source of truth for the API. The code-first approach allows for dynamic schema generation. You can generate your schema based on variables and templates to reduce code duplication. It's a matter of preference. There is no right or wrong option, and the AWS CDK allows developers to choose the approach they are more comfortable with when creating and maintaining their AppSync GraphQL API code. So there you have it. I hope you are able to successfully explain how AppSync can help you in your next development project. With AppSync, you can start effortlessly with your GraphQL journey on AWS. It scales with your business, and you just pay for what you use. It provides powerful built-in real-time and offline capabilities, allowing you to unify and secure access to multiple data sources, APIs, and services. Amplify provides fantastic development tooling and integrations with AppSync with the Amplify data store and the GraphQL Transform. Tools like the AWS CDK allow GraphQL developers to build AppSync APIs using either a schema-first approach or a code-first approach. Between Amplify and the CDK, you have powerful tooling, frameworks, and choices at your disposal to build and maintain your GraphQL API with AppSync. Here we have some useful links where you can access our documentations, you can access our AppSync community, also some resources like sample apps and customer testimonials. Thank you very much. It's always a big pleasure to present at re:Invent. I hope this was useful. And please join us. I think in a couple of minutes we're going to be at Twitch answering questions, and it's going to be a Q&A. And please connect there so we can have a chat about AppSync and GraphQL. Have a great day.